What is the decomposition of functions, or in other words, the change of variables? To understand this, we need to recall briefly what is the composition of functions, because the decomposition is the other way around. So if we start with a function which maps x into f of x, so the function f, and a second function that maps numbers y into g of y, the function g, then if we define the input here, the input y, as being the output of the function x here, then we are allowed to substitute f of x into g of y, giving us g of f of x, which by itself is another function of x. So to emphasize that, let me just say that g f of x is this composition is h of x. In what we are going to see, h of x is our starting point. And the goal of the decomposition of functions, as we see from this equation, is to find g and f in such a way that when you compose them, it yields the original h of x. To understand this more clearly, let's look at examples. Now, let's address the example number 1, which is our function h of x given by the square root of 1 minus x squared. You should note that 1 minus x squared is our mountain function, so you already know quite a bit about this function. So let's use it, because 1 minus x squared can only be above 0 as long as x is within minus 1 and 1. And if you remember, the square root function can only accept positive numbers. So the domain of h is given by this thing here. So what is the question at hand? Well, we want to decompose this h of x, meaning we seek the functions which map x into f of x, the function f, and the function g, which maps y into g of y. So we seek these two things, but with the constraint that g of f of x must be equal to h of x. Let me paraphrase it again. We want this composition in such a way that it yields the square root of 1 minus x squared for every x in that domain between minus 1 and 1. How are we going to solve such a question? First, let me make this clear. We want f and g such that this equation is true for every x. So our unknowns are f, the function f of x, and g of y. These are the unknowns. The unknowns are functions this time, not numbers. After that is clear, well, we can now employ on the solving this equation the generic strategy that we always use to solve equations, which is to observe the thing, the equation, try to guess what the answer is, and then, after our guess, we just verify if our guess is good. If it's not, we just repeat the process. So observing this equation, what we see is very important. On the left-hand side, we see the composition. But looking closely, what we see? We see that first we compute f of x. Very important. You have an x, you compute f of x. And then you compute the g of f of x. First layer, compute f of x, and then compute g of f of x. Because this has a layered structure, first you compute one thing and then another, is there such a pattern on the right-hand side? Let's look closely and see if there is such a pattern. Because if I look at this side, we focus on x. What is the first thing that we compute with x? Well, it's exactly 1 minus x squared. If you compute that number, then that whole number now is feeding into the square root, and you compute the square root. So this suggests to us that a good guess for us is as follows. We choose f of x as being 1 minus x squared with x belonging to this domain, and the second function, g of y, is exactly the square root of y, with y belonging, as usual, from 0 up to plus infinity. And this is how it's done. This is our guess, and now let's verify it. Well, I think it's quite obvious that it's going to work. Because if you substitute f of x here, so you substitute this thing here or here, we get g of f of x, which is equal to the square root of this thing, 1 minus x squared. But isn't that what you see here? Okay? Our guess is indeed correct. The three-step strategy that we had just employed to solve this equation is usually paraphrased quite differently in practice. Looking again at our equation, what we see is as follows. We look at it, you see the layer structure of it, and we recognize that 1 minus x squared is an entire variable, is a symbol for the variable. And to emphasize that, we call it y. So y now is by definition 1 minus x squared. As a way to emphasize that that thing is a number, the input of the square root. And as you do that, you do two things at one time. You not only recognize that 1 minus x squared is indeed the first function that you have to compute. Moreover, if you substitute this thing here, you get exactly the square root of y that we had defined here. Okay? This side is our f of x. Recognizing 1 minus x squared as a symbol for the variable tells you in one shot the two functions that are involved in this layered structure. And that's why we call it the change of variables, because after you substitute 1 minus x squared by y, you get exactly the second layer, g of y, and also you get the other layer, which is 1 minus x squared, which is f of x in this case. Now let's see another example. Now, example number 2. Consider now the function h of x, which is equal to the square root of x divided by x plus pi. We seek a composition of the form g of f of x. Again, we solve this just like previous example, so let's look at this time at the left-hand side and see whether there is a layered structure in the calculation. Looking at it, we start with x. What is the first thing that we compute with x? Well, there are two things, in fact, that we can compute with x. Either we can look at it and compute x plus pi and think of it as the variable, the new variable that you want to introduce on this function. Or you can think of it, the first thing that you compute is the numerator, so the square root of x. So let's take each case one at a time. First, let's recognize that this thing is the variable, so let's call it y is equal, by definition, x plus pi, which means that x is in turn, see, x now can be computed from y as y minus pi. As you substitute this thing here, what we get is square root here of y minus pi, and in the denominator we find just y. So this is our new function, our g of y. What is f of x? Well, this change of variables in fact tells us that, which is this thing here. So f of x is indeed x plus pi. Let's now check, because it's our guessing, let's check it through the composition f of x. So let's substitute this thing here and see what happens. Well, we get here the square root of y, but y now is f of x, so it's x plus pi minus pi, this minus pi, divided by x plus pi. But the pi's cancel, so it's the square root of x plus pi. So indeed we are correct. Let's now take our second way in which we can make a change of variables on this function, namely to recognize that the square root of x is in fact the new variable. By doing that, we write that y now is by definition the square root of x, but that in turn is equivalent to saying that x is equal to y squared as long as x is larger or equal to 0. Recall that the domain of this thing, domain of h, is indeed all real numbers, positive or 0. Now, substituting this thing on our function here, what we get is as follows. We get the y on top, and here y squared plus pi. So this is our new function, the g of y. G of y is given by this, while f of x is just the square root of x. To make sure that we are indeed correct, let's just now verify our guesses and see whether g of f of x recovers the original thing. So it is y, you substitute the square root of x here, and the denominator we get the square root of x squared plus pi, square root of x, and here, well, if you take the square root and then you square, you just essentially done nothing, so you just get x again, because x is indeed positive or 0, so there is no problem. And that's it.